Welcome back. This is lecture 7, titled Some Basic Physics Problems, or Some Basic Problems. So we're going to use some of the formulas that we derived in the previous lectures to solve some basic physics problems that we might encounter. The first problem is a problem pertaining to average speed, or average velocity. So the formula that we're going to need is that the average speed, or average velocity, is equal to the distance traveled, or the displacement, divided by the time taken. So delta x over delta t. And so what we're going to consider is a problem of, I'm going to try to do some art here. This will be a catcher. And then here we've got a pitcher who has thrown a baseball in a baseball game. So the relevant information that we need to know here is if he throws this ball, and we're also given that it took delta t, the time it took for the ball to go from the pitcher's mound to the catcher was 0.4 seconds. I'm going to write that so that we can see that. And you may know that the distance from the pitcher's mound to the catcher, or home plate rather, is 60 feet. So delta x equals 60 feet. That's this distance here. So we have all the information we need. So all we have to do is plug that into this formula. So the average velocity, or speed, would be equal to 60 feet divided by 0.4 seconds, which is 150 feet per second. Now, that's a fine answer, and it's correct, but we may want it in other units. So we haven't talked a whole lot about units yet, but one thing I will say is that when dealing with physics problems and thinking about physics problems, you should really think in units that you're comfortable with. Now, there are certain advantages to using the metric system, or as physicists would call it, the SI system. It's easier to work with. Converting between, say, kilometers and meters is a trivial task, just a matter of adding a few zeros. But if you don't have a feel for that, then you should try and convert to units that you do have a feel for. So 150 feet per second doesn't mean a whole lot to me, and probably not to you either. So let's convert this to miles per hour just to see how that would work. But to do that, we're going to need some conversion ratios. And let me just remind you what a conversion ratio is. So for example, it turns out that there are 5,280 feet in 1 mile. So that means that 5,280 feet is equal to 1 mile. Now if I divide both sides of this by 5,280 feet, then I will get that 1 is equal to 1 mile divided by 5,280 feet. Now, you probably know that multiplying a number or an equation by 1 is perfectly fine. It leaves it completely unchanged. So we don't change anything about the equation or the quantity involved, other than maybe the units, which is what this is doing for us here. So if I multiply 150 feet per second times 1 mile per 5,280 feet, which is just 1, right? Then this will give me this rate in miles per second. Now, we don't expect it to be very many miles per second. That would be unusual. Notice the feet will cancel, and we'll be left with miles in the numerator and seconds in the denominator. And so if I punch that into my calculator, see what I get here. Let's see, 150 divided by 5280, that's 0.28, we'll call it. No, excuse me, 0.028, 0.028, and that's miles per second. It's not a lot of miles. But of course, that's not miles per hour. We still have to convert the seconds in the denominator into hours. And we can do that through a combination of a couple of conversions. So we know that we're going to want our new units, hours, in the denominator. So we'll start like this. We'll say, all right, well, 1 hour in a ratio will go to minutes, 60 minutes. There's 60 minutes in 1 hour. And I'm going to multiply that times 1 minute in the denominator and 60 seconds in the numerator. And so you can see that that will cancel with that, and I'll get a conversion that will take me from seconds in the denominator to hours in the denominator. And so this is 60 times 60, that's 3,600, and that's seconds per hour. And so I can use that conversion factor in here. So 0.028 miles per second times 3,600 seconds per hour will give me what? Times 3,600. That's 102 miles per hour. So that we have a better sense for, because we know that 102 miles per hour is really quite fast. So that would be a super fast pitch. Not even sure what the world's record for pitches are, but it's probably close to that. Okay, so let's work another problem that's related to this. I'll leave the formula up here for average velocity or speed. And this problem is going to pertain to distance. So I want to imagine that we have a little toy car. That's a terrible looking car. That rolls across the floor for at some speed and for some time. Okay? So let's say that its speed is 2 meters per second, and that it rolls across the floor. It rolls across the floor for 3 seconds. So the question is, how far does it travel in those 3 seconds? Well, we can find that using this formula for the speed or average velocity by simply solving for the distance traveled or the displacement. So if I multiply both sides of this equation by delta t, I will get delta x all by itself on one side of the equation. And so I can get that delta x is equal to the average velocity times delta t, which is 2 meters per second times 3 seconds. And that will equal 6 meters. So the distance traveled, delta x, is 6 meters. Fairly straightforward, but you will encounter simple problems like that, if not as a standalone problem or exercise, but as part of a problem that you're solving. Okay, let's try another one. This time let's do one that relates to instantaneous speed or instantaneous velocity. And this one, let me look at my numbers here. Yes, we have a dragster. I don't know if you know what a dragster is, but it's these crazy looking cars that have like I think it's basically just a big motor, right? These pipes coming out. It's usually fire coming out of them. And then basically a driver's seat where a driver will sit and drive this thing. And these things are ridiculously fast. And the kind of accelerations that you can get out of these dragsters is, I hear, up to 4 Gs. So 4 Gs, that's an acceleration. We're actually going to consider it for, yes, 4 Gs. So what does 4 Gs mean? 4 Gs of acceleration means 4 times the acceleration that we experience on Earth due to gravity. And so you might recall that a G was about 10 meters per second squared. Are those the units I want to use? I think so. Yeah, I think so. So if our acceleration is equal to 4 times g, that will be 40 meters per second per second. So a lot of acceleration. And we're also going to be given the time of interest. So we're going to say, well, how fast is this dragster going at the t equals 4 second mark? So when t is equal to 4 seconds, how fast is the dragster going? So what's the equation we need to use for this? Well, we need to use the equation that the velocity is equal to the acceleration times the time. And we're going to assume, of course, that this acceleration is a constant during this time interval. Otherwise, this formula would not work. So all we need to do now is plug these numbers into that equation. And so this tells me that the velocity or speed is equal to 40 meters per second squared. I'm writing second squared this time. Times 4 seconds. And that will be equal to 160 meters per second, which is pretty fast, because I know 5-year-old kid is about a meter tall, so that is really fast, 160 meters per second. But let's see what it is in miles per hour. Since we've done that conversion before, we might remember that we need to multiply. Well, actually, we don't have the conversion yet for meters. I didn't give you that. We had feet before. There are 1,609.344 meters is equal to 1 mile. So that's a conversion we're going to have to use. So we'll multiply this times 1 over 1,609. We'll just chop it off there. Meters, and that's miles in the numerator. And so that's going to give us the miles per second. Let's see what that comes up as. So that's 160 divided by 1,609.099. So that's 0.099 miles per second. And we remember from last time, to convert the seconds in the denominator into hours in the denominator, we need to multiply this times 3,600 seconds per hour. And so I can punch that into my calculator. Times 3,600. That gives me 358 miles per hour, which is really fast. 358 miles per hour after just 4 seconds. That's some incredible speed. Okay, I think I have one more problem that I wanted to go over. Yeah, and this actually relates back to the last lecture that we saw, because what we talked about in the last lecture would be one way to solve a problem like this. And so this is an apple, so we're going to have a tree again. This is supposed to be an apple tree. And an apple falls a distance of 20 feet. A little tick mark like this is a shorthand for feet, and so I'll use it on accident a lot. And if I do, then just realize that's what it is. Inches would be 2 tick marks like this, but I'm going to just write feet in here now. So it falls 20 feet. Now we're going to use feet per second squared for the acceleration, the constant acceleration due to Earth, and that turns out g, if you use it in feet per second squared, is 32 feet per second, or per second squared. So we'll put that up there. We'll need to know that. And so an apple falls 20 feet from a tree. How long before it hits the ground? Okay, that's the first part of this problem. This is actually a 2-part problem that I wanted to do. And so the first part, how long before it hits the ground, is fairly straightforward to solve. We know that delta x is 20 feet. So let's write down the equation we got in the previous lecture for x as a function of time is equal to x naught plus v naught times t plus 1/2 g t squared. Okay? So this is taking t naught to be the moment that we release, the apple starts to fall. I'm going to move x naught over here so that we get x of t minus x naught. But this is just delta x. That's the distance that it's fallen. And this will be equal to, we're going to assume the initial velocity is 0. So that is just going to basically go away, that term there. And we're left with 1/2 gt squared. And so what I can do now is solve for t. Multiply both sides of this equation by 2 and divide by g. That'll give me 2 delta x divided by g will be equal to t squared, but I want t, not t squared, so I need to take the square root of this, and I'll keep only the positive root. And now we just need to plug in the numbers. So t will be equal to 2 times 20 feet, which is, 20 feet, and divide that by g, which is 32 feet per second squared, so we'll put 32 down here. And I could simplify that up here for you, but I think what we'll do is just punch this into the calculator and see what number it spits out. We get 2 times 20 is 40, of course. Divide that by 32. It's 1.25, and then we're going to take the square root of that. 1.12, we'll call it. So that's 1.12 seconds. So that's how long it took to hit the ground. Now, the second part of the question is related to the last lecture, and that is, if it falls for 1.12 seconds, how fast is the apple just before it hits the ground. Now you might recall from the last lecture that we actually derived a formula that allowed us to skip this step of calculating the time entirely. And then we could have just simply applied this formula that the velocity squared is equal to the initial velocity squared plus 2g delta x. And that would give us the answer that we're looking for. But since we already have the time, what we're going to use instead is the formula the velocity is equal to initial velocity plus g times t. The initial velocity, of course, is 0, so we just need to plug this in as 32 feet per second squared times the time of 1.12 seconds, and that will give us, yes, this is going to give us a velocity of 36 feet per second. And we could, of course, convert that into miles per hour if we wish to do so. And we've already done that before, so I think we'll skip that here. But I could show you real quickly that we get the same thing if we use this expression here. So again, the initial velocity would be 0, so we just need to calculate the square root of 2 times 32 times 20, and that gives us 36 feet per second as well, which is somewhere around 25 miles per hour. Okay, that's it. The next lecture we'll do a Q&A where we'll sit at a round table and discuss some physics questions that relate to what we've talked about in 1D kinematics. And we'll get some student participation, and so we'll get some idea of the kind of questions that you may have when you watch these videos. All right, thank you very much.